Log on, tune in, find out. Another good idea from Cambridge.
He's going to talk about that stuff. So, Christian.
Thank you very much. That stuff is key management and storage encryption. So it's a topic that I have come into contact with over the last few years, yeah? And the subject here is whether or not our cryptographic theory is relevant for practice. I will look at this for certain aspects under certain themes that are relevant for storage encryption and key management. That's tweakable encryption, something that has been come up, and an encryption mode has come up in the notion, the relation of disk encryption. Key management, that's an important topic as well, where the cryptographers usually go to sleep and say, let somebody else do the key management. And key wrapping, that's something that's related to key management. This is in connection, this is in joint work with a number of people from our team in Zurich and at IBM Research. So, tweakable encryption. Oh, now OpenOffice installing, huh? Thanks. Okay, we can have it in OpenOffice as well. Okay. Been there before. No, but thanks. He just installed OpenOffice since I said I have OpenOffice. So we'll see if it makes a difference. We can go back to the PDF. It doesn't work, huh? So encryption at the block layer. Block layer is how your data gets ultimately stored. A disk device, a storage device, manages storage space in chunks of 512 bytes. They're called sectors. And you can arbitrarily address one of them. That's how the disk device is inside basically every storage system work. The storage system in between this, there is a stack of layers that go from a file system, and on top you have your application, and you have a file system that's shown here on the left. You have an object layer, an inode layer in the file system, and at the bottom you have a block layer where the files are chunked into 512-byte blocks or sectors, and then they're written to disk. And then the question was that came up a couple of years ago, or the demand was, let's encrypt here those blocks. Yeah. So as a cryptographer, we could have known how this works for a long time, because this is just block cipher, symmetric key cryptography. You wouldn't have to invent public key cryptography for this. But the problem here is that there is actually no extra space if you want to do this in a transparent way. So things like that didn't matter for communication encryption, like TLS or so, that you can add a bit of padding, that you can add some initialization vectors. This is not possible. And there has been a IEEE Security in Storage Working Group addressing such topics. And then the first idea that people came up with, let's use CBC mode. That's what is the default operation, the default block cipher encryption mode. We need a random initialization vector, as we are taught in Crypto 101, and there is no space to store this. So we have to derive it from somewhere, and you better not take something that is predictable. And but the only thing that you have available at this layer is the address of your sector that you have to encrypt. Yeah. So you can take this one. If you take this address, you're not using this address as the IV. You are going to encrypt this address with the key, and then you get something that's unpredictable. At least now that this where the problems will start. Yeah. So this this IV is what you can use as, you can derive this IV in such a way, and then you are fine with encrypting the rest in CBC mode. Now this when there is an update on the disk, an update to the stored data, say you change a byte in a file somewhere, this is going to change at least a cipher block, an AES block in that case that we do use, on the disk. And then with CBC mode, you would leak, in this case, the first change you did in a 512-byte sector. You would not leak what changed afterwards, right? If an adversary is able to see your disks, your disk blocks, and then you did some work, and the adversary is able to see this again, you would leak the first one of those that you had changed. And that would be an adversary restricted to a passive attack. If an adversary is able to mount an active attack, it would mean that, well, you come to a conclusion that CBC mode is not so good, because you can trigger changes or specific changes to particular blocks, because you can change the ciphertext in a particular way that will have direct influence of the same kind on the decrypted thing. You will randomize the next block to be decrypted, but that could not be relevant for an application. The application could just simply ignore this. So you have control. In cryptographer's terms, this would be a malleable. This would be a malleable crypto system. So there are certain problems, but you have to also remember what this would take. Usually, the disk or storage device is inside your laptop, and the key is sitting in the kernel somewhere low level in the operating system. So if somebody has access to this disk drive but not access to the key, what is the security model that this is realistic for? Perhaps you can think it's when you have to give your laptop at immigration, they go and change some blocks on the disk, and then well, if you have to give your at customs inspection or immigration, if you're a Swiss bank representative traveling to the US, then this is a threat model that you could perhaps have. You have to give your laptop to the to some authority, and it comes back, and they will be able to trigger some changes on your disk. Is that realistic? Well, for most people's laptops, it's not so realistic, I would say. But there are other models nowadays that come up where this could be more realistic, actually. But anyway, so this is one thing that people have done. Then people have started to look at, have recognized this problem that the CBC mode would actually not be an ideal encryption of this sector, of this 512 bytes. Liskov, Rivest, and Wagner have come up with the idea of tweakable encryption, where you would not use one block cipher or sector level cipher now. That's the same with the same key, but you would basically make a family of pseudorandom permutations out of this by introducing a tweak. So you have a family of cipher calls in that sense that's indexed by a public tweak. That could play the role of the of this initialization vector for CBC. But the idea is here that if you take a different tweak, you get a completely independent pseudorandom permutation applied to your input data as it goes to the output data. And so that's been suggested for use in this disk encryption world. And it makes sense, except that now reality comes back and people have realized, well, how do we implement this actually? People have started to look at particular modes. And the E box that I've shown here is just a block cipher, 16 bytes, but the sector is 512 bytes. So there are two families of such tweakable encryption modes actually. One is narrow block, which is a construction that first construction of this kind came up already with that paper. The later constructions I'll just show, but the idea here is that you take one AES block at a time and encrypt that with tweakable encryption. Of course, you need an additional index called I here in the sector that enumerates those sectors to make these permutations independent of each other. That's so good. So far, so good. But now, if you think about the passive attack we said before, somebody is able to watch what changes. If you change a bit or a byte somewhere in your file, you will leak more than for CBC. Actually, if you change 2 bits or 2 bytes in 2 locations, because you will not only leak the location of the first block that has changed as in CBC, but you will leak every 16-byte block where something has changed. So in some sense, this is a reduction of security. But for the active attacks, of course, you get better security, because inside one of those narrow blocks here now, the adversary has no control. If you would change some bit on the disk, flip some bits on the disk, it's completely unknown to the adversary how this will affect the plain text that will be decrypted. So this is better, not in a usually quantifiable way, but better. And there has been this XCS AES mode introduced. I guess this must be Phil Roggaway that are there, but there's a lot of people here in the room that know much better about this than I do. But definitely there is a construction where you encrypt once you tweak or the sector address, and then you do some exponentiation in a finite field of with 2 to the 128 elements, where if you run sequentially through this whole 512 byte block, this is quite efficient. So you take you do this, but but you are getting the security notion here is independently encrypted, tweaked 16-byte blocks. This has indeed been standardized by the IEEE 1619 effort and the Security in Storage Working Group, and it's also made it into a NIST standard more recently. And so this is actually implemented nowadays by the disk encryption products and by kernel level encryption software, etc. On the other hand, the original idea could have been also that you take this whole sector and you encrypt the sector at once. Yeah? You take one sector, 512 bytes, and make it another sector, so that you would not leak in which 16-byte block you have changed something. This goal has been more elusive, yeah, because you have to somehow connect the bits in the first block to bits in the last block. The whole thing should be a 512 byte block cipher in some sense, and you wanted to construct this from a 16-byte block cipher. There have been some suggestions for this. Two modes here, EME2 AES. I think that's from Phil Rugaway again and Shai Halevi. The cost of those, however, is larger, about twice the cost of AES for one AES block. So there's a factor of 2 overhead, and I'm not quite sure what it is, but I came to the conclusion that this is what must have reduced interest by practitioners in this, because the standardization efforts of this wide block tweakable encryption, they have stalled. I'm not aware of any product that implements this in practice now, and so this is already too much apparently. Yeah? This because you would have to pay the cost of encryption twice, not just once. So as a summary of this state of the art in disk encryption modes of operation here, we could use CBC mode, yeah, for a passive adversary. As I mentioned, you could localize the first change in every disk sector that you did. Whether or not this is relevant remains to be discussed further, perhaps. Yeah. But what is actually used in practice, the narrow block tweakable encryption, this AES XTS mode that all the disk encryption products now implement, they leak more. They leak wherever you actually encrypt it, where they leak the position of every byte that you actually within a 16-byte block. Whereas the wide block, that would be the best possible thing to achieve, because the file systems can address randomly, can change randomly, arbitrarily I should say. They arbitrarily change disk sectors at a time. This would be the best possible thing to achieve. That is not implemented. Yeah. An active adversary, on the hand, could mount more serious attacks against device-level encryption with in CBC mode, because you could not only change a few bits or induce controlled changes, you could also move some blocks around, and they will be decrypted again when they have moved to a different place correctly. That's the reason behind this, is that the same key is used for the whole disk device, but the files and the data may belong to different users, because the encryption happens in the kernel, where it's the same key for all the different users. Again, if this is a realistic attack or not, one can debate about this. But definitely, an active adversary in the tweakable encryption modes, an active adversary has no control over how something changed will be decrypted, and that's their motivation of existence. How realistic are such active attacks in practice? I would argue that for laptops and computer systems that you can see and touch, right? This means basically everything that you can walk away with or you have in your home somewhere. The active attacks are not very relevant, yeah, because you must have an adversary that comes and touches something here, or you should leave the device for a few minutes somewhere else. Somebody does something to it. In a cloud computing environment, or where this is on a server somewhere, the storage space is not produced like this normally, because a virtual machine may have a disk image mounted from a file system somewhere else. And in this case, it's more realistic that you can have an active attacker, because somebody, the threat model is no longer monotone as a pyramid, so that the further down on the level you go, the more security you have, the more assumptions you place this. Because you could consume storage space from somewhere else in a cheap outsourced storage, and your virtual machine has this key inside that does the encryption, but the storage is less trusted than this. This might be possible in a cloud computing environment. Yes?
What is a sector in that setting?
A sector is a sector.
Even for the cloud?
Well, because in the cloud, if this machine is a virtual machine, its disk is a file on some big file system. But this machine talks to this disk by reading and writing 512 byte sectors or 4 kilobyte sectors or something like that. But everything is virtual. There can be multiple layers of such virtual things on top of each other as well. Anyway, that's something that has not, the state of the affairs here is that the justification for the theory was given, but people have not done the full work, in my understanding. Another question?
So I could add a little bit to that. So the XCB mode of operation is in use in fielded products.
Yes.
But not many, and I participated in that working group.
Okay.
And my impression is that most of the participants were, satisfied with the narrow, and once that had gotten some adoption, they resisted the,
Yeah.
resisted the need. Perhaps it met their needs because they were their application was laptop.
Okay, thank you. That is my impression as well. Most people were satisfied with the narrow block and didn't want to go the extra work for the wide block.
Hasn't the standard issued?
Excuse me?
Hasn't the standard issued for 1619.2 for the wide block?
That I thought not.
If it hasn't, then it's just in the IEEE paperwork.
Then it's in the paperwork. Okay, thank you. Okay, I would like to go on to key management. That's a topic that will come back in the later part of the day as well, which is usually where cryptographers stop and they say, I have there some keys, please take care of them, yeah? Or the paper starts with, let there be some keys of this and this kind. And in practice, this is usually a mess because you have a lot of different systems and they usually come with their own proprietary key management schemes. And a couple of years ago, people started to address this with a vision of creating uniform syntax, uniform language to interact with on keys with different applications. And they also in an effort that we were participating in, we were creating this vision of a uniform key management system with a key management interoperability protocol as it has become to be known. So the idea here is that you can have an outsourcing in that sense to a centralized service in your large company that would take over all key management needs for these different systems. This is a very specific standard that has come out. It's called OASIS Key Management Interoperability Protocol. That has come out 2 years ago now, or 1.5 years ago. OASIS, in case you didn't know, this is the organization behind XML. So if you have ever heard of XML, that's OASIS. However, this standard does not use XML. It has to be implementable on a tape drive in a firmware, and the reason for this, and this basically ruled out the use of XML for describing this. And we can also do this in bits and bytes. Anyway, this is a client-server protocol, so a language for a client to invoke operations on keys and attributes on a server. And so the keys can be all kinds of symmetric keys, public keys, certificates, and in that sense it's more general than existing syntax and existing languages for key management, because X509 dealt with public keys and certificates, other standards dealt with symmetric keys, and this one here, to our knowledge, to our understanding, is the first one that addresses this whole scope of public keys, private keys, certificates and everything. Yeah, it's not meant to do cryptographic operations, but they cannot be completely avoided. So a bit of the history of this is that from this work on encryption of storage devices, or more specifically encryption of tape devices, so tapes, the content on tape can be encrypted, And if you want to connect tape drives and encrypted tapes from different vendors to a key management system, you need some way to do the key management in an interoperable way. And that's what led to this. And that's why also you see a lot of storage vendors, companies behind this effort, which started as a behind-the-scenes effort where a smaller number of those companies got together and said, let's formulate something and then let's try to get this standardized. Because other working groups, other standardization groups had also key management efforts, but they got lost in the details. This 1619.3 was a key management effort that didn't go through because it got lost in the details. So there was a behind-the-scenes effort, and then a group of companies took this to a standardization gremium, and the initial submission to this was already version 0.99 of the standard, and it took a year or two to get this then published to make this standard out in 2010. Yeah. So today there are several vendors in the storage space that support this, at least what functionality, its part and functionality that concerns symmetric key handling and simple RSA and public key handling. The standard allows to define arbitrary types of keys. You can have objects which can be public keys and symmetric keys of this type. It has many different attributes to talk about the life cycle of cryptographic keys that come into existence, that have to be retired, the keys that are expired, etc. There are attributes that should govern the usage of keys, how much data you have already encrypted with a key, etc., etc. But what concerns us here is that a server that speaks this protocol is a key management server that is accessible over a network, and in that case it becomes a cryptographic server, yeah? Some entity that executes cryptographic operations on behalf of clients that are invoking operations on it. And in this case we need to look a bit closer into these operations. So you can create a key, you can derive a subkey from a parent key. These are all symmetric keys for that purpose. You can store key that you give in clear text. You can also import the key that you give to the system in wrapped form. Wrapped means encrypted under another symmetric key. In this world where you have hierarchies of symmetric keys, such that you can transport keys from one system to another system, and they're always guarded by a super key, a symmetric master key. And there are other operations then to manipulate attributes and so on. But as the picture shows here, some of these operations are actually cryptographic, the ones shown in red. The other ones are straightforward database operations. The ones shown in red here, they involve some cryptographic operations on the server, and that plays a role because the server has to do some crypto nevertheless. Yeah?
Do you enforce the hierarchy?
Do we enforce the hierarchy? That's a good question.
If you have circles, you have issues with circle.
Yeah, if we have circles, we have a problem. If we have an issue even before that.
You should have a tax.
Anyway, so let's just go there. So we will. This is an access control model for the KNIP server that we formulated. This goes beyond what's in the standard. So we formulated that there will be different users that can trigger different operations on keys that they sort of own or keys to which they have permission on the key server. We think there could be an arbitrary users, like special users, like any user. There are permissions that are usually linked to operations. You have a permission to derive a key from that key. You have the permission to use this key, to destroy this key, or you have the permission to read the clear text bits of this key. That's a special permission that requires special privileges, obviously. Yeah? And so an object in this server has an access control list that simply says there's a user has this permission or another user has that permission. And now a key server, as I mentioned, because it has this few cryptographic operations, it becomes a security API or a cryptographic API, and people have looked at this for a while already because such APIs have been out there in the field in the form of cryptographic tokens. These are hardware security modules that have been used for using cryptography in adversarial environments, right? Bank machines or SIM cards and things like this. Except here we have now a clear need to support multiple users, multiple different users that access this. And this is actually the new element here. So these cryptographic tokens are usually hardware shields that give the security officer a warm, fuzzy feeling that he can sleep well at night, that these keys that guard the financial transactions of its institution are not exposed to an adversary. And the whole reason for using those is to separate the administration of systems, the administration of a server system, where there might be several admins for the server who control what the system does there, from the administration and control over the cryptographic material. So there's a security officer in large organizations, obviously only, that has this special privilege to look at this, where 4 eyes principle and many other things have to be enforced, because such keys can be used to create money, to print money, or create digital money. Yeah? So keys in this world must never leave the cryptographic hardware boundary. This is a picture of some cryptographic of some implementations of this. You see again all the big vendors in this space do have expensive ones, as these are the ones on the top, but also a TPM is a cryptographic security module because it gives a hardware boundary around a key that is intended to be put on a laptop. So we were wondering then, or in this world you were wondering, why do we need those and what are the rules for accessing this? And the usual rule is that cryptographic keys shouldn't be exported from these devices, and as I said, it introduces this separation between the security officer and the server operator. And now we look at the formal model for interacting with these cryptographic tokens in a more formal way. Yeah? So we introduced a model here where we have different users, and we can trigger invoke operations on those keys that are residing in those secure hardware boundaries. With the idea again, that is nothing else than our key server. Yeah, there are some standards for token interfaces. This RSA PKCS 11 is a very popular interface that has been out there for 20 years or so. IBM has developed a common cryptographic architecture that's already 30 years old, that came out in the 90s or even older. That doesn't even include the concepts of public key crypto. And researchers and practitioners have looked at these interfaces, stateful interfaces, and discovered some problems with this. And thanks to the efforts of Ross Anderson here in Cambridge, also in the efforts of debugging the bank's crypto infrastructures, these problems have found a wider audience in the scientific literature, right? So the problem is that some of these APIs intend to implement some security policy, but this is not actually implemented and backed up by the implementation. Yeah. So, for example, here is an example from the PKCS 11 interface. There is a flag which you can label a key that's residing in a PKCS 11 token as sensitive. And it means, it's what the documentation says, such keys should not be exposed in clear text outside the device. So obviously the read command for such a key will fail unless you are the super user. But the most implementations, or at least the standard here, does not restrict the following sequence of operations, which are: create a new key in there, and this new key is not a sensitive key because I created it, so I can read this key out. Then wrap the sensitive key, this means encrypt the sensitive key under the newly created key that I can read out, and then something wrapped can be exported. There is no explicit check for this. And this is, of course, means that I can get the bits of the sensitive key out of this interface, out of this token. And I shouldn't be allowed to do this. That's at least what the the impression I get from reading the documentation. It's not exactly clear if this is a specification you have to implement or not. Anyway, so this is a problem in the sense that these tokens would need to implement a much more sophisticated security policy than they actually do. And when we're looking at this with the goal of constructing a much more complex key server, we wondered why this is the case here. Why are there problems showing up? We wanted, after all, to construct a model where multiple users interact concurrently with such a key server, and why is there this problem? Well, it's more complex than the usual access control problem because those keys have, some of those keys have cryptographic relations to each other. And the simple access control model, where you treat every key independently of each other, this does not reflect such dependencies among keys that have been created through cryptography. And so we simply set out to model those in a paper that we published 2 years ago, and we call this a strict access control policy that allows us to keep track of such dependencies. So we build a model in the device. The device has to be made stateful, that now tracks which keys depend on which, because a key, like the red arrows here, a key has been derived from a super key, or because in the blue arrows here, you have wrapped a key under a wrapping key. Wrapped means you exported it also. You exported from the device the encrypted key under a super key. And once we have such a concept, or in order to express this concept, we need now more attributes in the device. We introduce some attributes here in this policy. The strict flag basically tells if an object is subject to this strict policy. We introduce a set of dependent objects that are all those objects whose cryptographic key material I can derive from this object. Yeah? And there is a set of ancestors, which are those objects from which I can derive the key material of the object I'm looking at here. And there is also another orthogonal component, which are the users, which are entities that have already read cryptographic material of some key, or are empowered to derive the cryptographic material of a key that is represented here. And this means, of course, again, that there has to be state information maintained in the key server. So, and then we formulate a strict policy that can say, if an object is under this strict policy, I want to be able to check such dependencies. If we use this basic policy, then we get the default where all the objects are independent. So basic authorization rule would simply be, you can ignore most of this thing with basically saying, for user U to has permission P on an object O if the tuple U, P is in the object's access control list. And the rest implements special logic for creators and owners and any user in the system. So the implementation of a read command becomes now to check whether or not this object obeys our strict policy, and if it obeys, if it's under the strict policy, we have to check for all the dependent objects of this object that the reader of this, the user that tries to read this, has also the permission to get the bits of the dependent objects. And if this is the case, we will permit the operation to be executed. If this is not the case, we will just say no. And the admin who wanted to do this operation, how can he fix this? Well, it's simply something that the system makes, where the system makes obvious that the problem is about to happen. If the admin wants to do the operation nevertheless, it has to go back and give read privilege to the user that tries to do the operation for all the dependent objects. And maybe by doing so, it will become obvious to the admin that there might be a problem that it is going to happen here. But it basically is a way to enforce such access control and make it explicit. As I mentioned, there is also a side effect, there is state, because now the reader has obtained the cryptographic material of this key, and we have to note that all this key and all dependents for this key and for all its dependents, this user is now a new reader. So this user has now access to these bits, and this has to be considered in further in further access control decisions. Yeah, there is the more complex operation of an export, which means to wrap a object O under an object W. So this is, think of symmetric keys for simplicity, and then you need the permission to export. Here we need the permission to wrap, to use W as an argument to the wrap operation, and then you also have to check that for all the readers of the wrapping key and for all the dependents of the key being wrapped, the corresponding permission is present, such that all the users who have already known this key are not becoming have the necessary privilege to know this the bits of the key being wrapped, because they might know the bits of this key, and the side effects are even a bit more complex here. Yeah. So in the interest of time, I'm not going to go through all these details here, but I would like to stress that wrapping of this form requires an authenticated encryption, because an authenticated encryption of the key together with some associated data, as it has been called. So together with some side information that will be the attributes that we store here. Because when you go to another key management system and then you will do the inverse of export, which is import, it will take the attributes that have been written in the wrapped blob, and it will put those attributes inside the its own database. And of course, if you could modify and change these attributes on the fly, you could subvert the security policy that we are trying to implement here. That has also been recognized, but not in a very formal way in the industry. Yeah. There are some special cases for delete, but anyway, I would like to discuss this model here more. This is a model we've introduced some time ago with one key server only. It's not clear how you would extend this to multiple key servers, because the state information of who executed which operation is obviously critical. If you did an operation over here, it might suddenly deny your permission to do an operation over here, and these tokens would have to synchronize their state immediately, which is not feasible in practice. But of course, you could come around this by corresponding. You could perhaps partition your space of keys and tokens such that such things become no longer possible. But this is left for future work. The interest, so we have implemented some prototypes of this, also shown how we could integrate this with a KMIP specific key server by using compact representations of which user is reader and which keys are accessible to which user. We have not experienced any problem of state explosion. We do not have to keep a history of all operations. We can simply maintain these data structures. For a server, this is kind of efficient, but we haven't been able to test this in the real world. And that leads me actually to the connection to practice again, because this is in some sense practice-induced theory research, and then the question is, how much influence does this have on practice? And so far I have to say not much, because these interfaces, they have been, at least for the IBM CCA interface, has been there for about 30 years, and it's not easy to simply come with a completely new approach to change this. And so it would take, I would say it basically takes a completely new wave of products to implement something like this. On the other hand, when you talk to people in the field, they're mostly aware of these problems, and they will say, oh yeah, of course you cannot do this, of course this is insecure if you allow this, and so on and so on. And that's what we never do, that's why we never do such and such. But then, why is this the case? Is this just the collective wisdom of the security officers? And should this be, is this black magic that only those people know? Or shouldn't we be able to take this and make it into a sort of more formal representation, also give these guarantees to those people who have not studied these dependencies in such great detail? So the practice here in this area moves very slowly. This is also connected, of course, to the fact that there is hardware involved, cryptographic hardware devices, that when you think about the typical ATMs out there where you get your money, there is still DES working in there. I mean triple DES, but it's not AES, right? And these things move quite slow. And that brings me to the third part, the last part of my talk here, which is the notion of key wrapping. That has mainly found applications for exporting keys in hierarchies from one token to another token, right? And in this case here, you could simply say we encrypt the key like we encrypt our plaintext, right? And somehow the requirement people have put up on this is that since the key is already random, yeah, it's really something random that we encrypt here. So we do not want to have extra randomness like an initialization vector. So for some, and then we can also, maybe we do not have a random number generator around somewhere where we want to wrap a key. Well, as a side remark, this motivation is not a good motivation for when such a cryptographic token wraps the key, because at least the powerful tokens, they are those where the keys of your enterprise are generated. These are not the tokens that are deterministic like cheap RFID devices. But anyway, so we accept this motivation that the wrapping should be deterministic, and it should encrypt some key together with associated plaintext, and it should implement an authenticated encryption. So you cannot change this without being detected. Yeah. So, and it should also ideally not expand the ciphertext by anything, not by any bit. Yeah. And yeah, another motivation, as it's been stated in a recent NIST proposal, is that if you use something, paraphrasing this here, if you use something completely different to encrypt your keys from how you encrypt your data, we might be more secure. But anyway, so this concept can be traced at least to these control vectors as they exist in this IBM CCA, the Common Cryptographic Architecture Framework, where you have control vectors that represent the bits, the attribute bits that exist, that govern the usage of those keys inside these tokens. And the theory there of Matthias in 91 says you can hash this, and then you XOR this key, this control vector to the key, or the key encryption key, and then you encrypt with a normal block cipher your key. Where you can also implement this hash by the identity. It doesn't need to be a real hash function. Yeah. So actually, they will just have 64-bit CVs, and will just XOR this to the key. If you think about this in terms of what it does, it's not exactly clear what security notion in modern cryptographic terms this gives. I think this is also left for investigation. But this is it's a form of tweakable encryption, because this control vector, the attributes of the keys, will govern what happens with this. And if you would try to decrypt or try to unwrap the key with different attributes, you will just simply invoke a different key, which has, so the key that you recover has no connection to the key that was wrapped. But not only IBM has this, there is also key wrap specification has come out from NIST. It's based on an ANSI X9 specification. It's like a small Feistel network where you have about 12 block cipher calls per actual bit, per block that you actually output. So it's not exactly clear what it does, and I'm sure Tom can correct me later, but Tom Shrimpton and Phil Rogaway have looked at this, trying to find out what this should actually implement, what the security notion is that is implemented by this beast, and they were unsuccessful in the sense that they were not able to clearly state a model in which this makes sense and is the only solution. In contrast, they came up with a model that made sense to them in this paper, and they proposed a much simpler thing called SIV that achieves their notion of security in the cryptographic formal sense. Nevertheless, standardization process continues, and this NIST specification was just issued last summer, and so this shows that there has been some feedback between this, but practitioners in this case have not taken up these other suggestions for this. Yeah. In KMIP, we also were faced with the task to specify key wrapping, And we didn't look at this in such a restricted setting because we said we have extra bits and bytes available, so we are not restricted to be deterministic either. And we just simply said that you can wrap a KMIP object with any authenticated encryption mode if you want to be secure. And for those who do not want to be secure, we also allow you to wrap it with encryption only. And we ignored these other key wrapping formats so far. Okay, so that brings me to the conclusion of this excursion into key management and storage encryption and key wrapping. It shows how some of the theory was triggered by practical demands, some of the things you can derive from practical demands, and when you try to look inside what people do in practice. You can have both, right? You can have practical demands that lead to new theory, like the disk sector level encryption. You can also have theoretical things that are suddenly now relevant in practice. It does take some theoreticians that have a sense of reality, so you're connected to what actually is possible. Practitioners that we have also come to recognize in industrial research, practitioners, implementers, product groups, they never read papers. They might look at your prototype if you stand in front of them, and yeah, if there's, but what really impresses them is when another company just comes up and gets all their business, like as a startup, and gets all their business because they have a better product. Yeah. So that's my conclusion of this. Yeah. Thank you.
Okay, we have time for a quick question. Anyone? All right.
I have a small interest in standards. I
Yes.
was the editor of the ISO authenticated encryption standard. And it occurs to me that the replacement for AES key wrap, by the way, AES key wrap is in the ISO standard because the US wanted it to be. The replacement for AES key wrap was not, as far as I'm aware, ever submitted to the ISO process. Now, if you or others believe that it would be good to promote this algorithm over AES key wrap.
Okay, so you're saying that theoreticians are also not interested in the standardization, which is a prerequisite of getting their things out there.
Well, maybe not a prerequisite, but it kind of helps. I
Yes, it definitely helps because the practitioners will also then only implement the things that are in the standard, and when there is a standard, they know what to implement, right? Yes, okay, that's a well-taken comment. Yeah.
I mean, I'd be happy to take on board anything.
Okay. Well, I have to admit that it's not my main thing, so I had to learn a lot of these things about the block cipher things as well. Yeah, and maybe there are some other things in the room more familiar with block cipher modes of operation and the relevant theory.
Quick
That
question
we
for
should
Dan,
talk
then we'll move on.
Well, just as a follow-up to that last comment, what does somebody do writing a paper to propose something to ISO? I thought it was only for people who pay to come to the meetings.
No, just write to me and I'll fix it.
You could pay him, I guess.
I said that was the. One quick comment.
You man, Carl, you.
No, not at all. You have these things at the end where you say what practitioners really pay attention to. You mentioned maybe prototypes, but definitely startups.
Yeah.
My experience is that they also pay attention.
Can you speak up? We can't hear you back there.
Oh, sorry. My perception is that they also pay attention when you break something.
When you break something.
Break it in a particular way. So
Yes.
I encourage everybody to go to this bloody ANSI, whatever it is, or the key wrap thing with the 12 AES calls, and try to cryptanalyze it. I guess Tom probably has had a good look at it.
Yeah, we did try a bit. We didn't find any real tags, but we also
I think
didn't find any
the
real
paper
motivation
says
for
it-
what they did.
Yeah.
Your paper says it may well be secure or something like that.
Maybe, but we don't know.
Yeah, okay.
Find any real
I think
justification.
it looks complex enough that it looks complex enough to me that it's actually difficult to find some issues.
More complex, the better.
Yeah, the security through obscurity. Yeah.
Yeah, that's exactly the discussion, the underlying theme that we have here: security by obscurity versus security from a clearly defined practical, from a clearly defined theory. But on the other hand, the practitioners sometimes I'm thinking about the Leichenbacher attack on RSA OAP, right? In that case, you could say Well, it's still secure. Not on OAP, but on RSA padding. That was not secure, but then the OAP format was promoted, and it didn't have a proper security proof. But people came up with a patch for the proof nevertheless, and so sometimes the theoreticians will then find new models, refined models that more realistically allow them to show why something that is thought to be secure in practice is actually secure. So that's also why theory changed.
No one uses
Yeah.
And still we don't.
No one uses it. No one uses it.
And still we don't use it.
Okay, so let's move on. So thanks, speaker, again. Thank you.